There's a comet out there capable of erasing every city, every forest, every trace of human civilization in a single afternoon, and nobody's talking about it. Right now, millions are obsessing over 3I Atlas, an interstellar visitor that poses zero threat. Meanwhile, Comet Swift Tuttle, a 26-kilometer monster officially designated as the single most dangerous object known to humanity, orbits in silence. It moves retrograde, meaning it would hit us head-on at 200,000 miles per hour. The impact would release 27 times more energy than the dinosaur extinction. It's not theoretical. It's real. It's massive. And it's coming back. You'll want to follow along as we separate genuine danger from sensational distraction. Subscribe now so you don't miss any single bit as new data about Comet Swift Tuttle, including the dangers it poses, continues streaming in. The cosmos has real threats hiding in plain sight, and we're here to expose them. Right now, at this very moment, millions of people are staring at the wrong thing in the sky. They're watching a cosmic sideshow while the main event rehearses offstage, unnoticed. They're counting grains of sand while a tsunami builds on the horizon. The internet is ablaze with talk of 3I Atlas, an interstellar visitor currently passing through our solar system. Social media feeds overflow with grainy telescope images. Amateur astronomers track its every movement, and conspiracy theorists weave elaborate narratives about its origins. Meanwhile, asteroid Apophis dominates the headlines with its upcoming close encounter in 2029, close enough that it will pass beneath some of our satellites. News outlets breathlessly report each new calculation of its trajectory. Reddit threads spiral into thousands of comments debating whether this is the end. TikTok videos promise to reveal what NASA isn't telling you, but here's what nobody seems to be saying out loud. Neither of these objects will kill you. Neither will end civilization. Neither deserves the panic currently being lavished upon them. 3I Atlas is fascinating, certainly. It's only the third confirmed interstellar object we've ever detected passing through our solar system, following the famous Oumuamua in 2017 and Comet Borisov in 2019. It arrived from the infinite dark between stars, carrying with it the chemical fingerprints of another solar system entirely, perhaps from a planetary system that formed around a star we'll never even see. Scientists at NASA and across the globe are tracking it obsessively, not because it's dangerous, but because it's an unprecedented opportunity. Think of it as a message in a bottle thrown across an ocean so enormous that the bottle traveled for millions of years before washing up on our shore. The closest this interstellar wanderer will ever come to Earth is approximately 1.8 astronomical units. That's about 170 million miles away. For context, the Sun is only 93 million miles from Earth, which means 3I Atlas won't even come as close to us as we are to our own star. It's not headed toward us. It's not slowing down. It's on what scientists call a hyperbolic trajectory, meaning it came from outside our solar system, and it's leaving, never to return. It's just passing through, and it's doing so at a distance that makes any collision utterly impossible. Yet planetary defense networks worldwide have activated to track it. Space agencies are running drills, practicing detection and response protocols, refining their mathematical models. Why? Not because 3I Atlas poses any threat whatsoever, but because it's an excellent training exercise. It's fast, it's unusual, and tracking it helps prepare systems for the day when something actually dangerous appears in our telescopes. Then, there's Apophis, named after the ancient Egyptian god of chaos and darkness. In 2029, this asteroid will pass within about 19,000 miles of Earth, closer than the ring of geostationary satellites that orbit our planet. You'll be able to see it with the naked eye as it streaks past, a brilliant point of light moving visibly against the background stars. It will be spectacular, historic, and completely harmless. NASA has calculated its trajectory with extraordinary precision. It will not hit us. Not in 2029, not in 2036, not ever in any foreseeable future. So why the obsession? Why are millions of people losing sleep over objects that pose no danger? Perhaps it's the same reason we slow down to look at car accidents on the highway. Perhaps it's because the human mind struggles to properly assess cosmic risk. We're evolved to fear the rustling in the bushes, the shadow in the dark, the immediate and visceral threat. We're not equipped to evaluate kilometer-wide rocks moving at tens of thousands of miles per hour through the vacuum of space. Or perhaps it's because we're looking in the wrong place entirely. While everyone watches 3i Atlas and Apophis, while the internet churns out doomsday scenarios and clickbait headlines, there's another object out there that actually deserves the title most dangerous. It's not mysterious. It's not interstellar. It's not even particularly exotic. But it is genuinely, scientifically, mathematically terrifying in a way that 3i Atlas could never be. Its name is Comet 109 P/Swift Tuttle, and it is the single most dangerous object known to humanity. You've probably never heard of it. If you have, you've likely forgotten it by now, because Swift Tuttle doesn't make headlines. It doesn't trend on social media. It doesn't inspire breathless YouTube videos promising to reveal what scientists don't want you to know. It's been known to astronomers since 1862, when Lewis Swift and Horace Tuttle independently discovered it during one of its periodic returns to the inner solar system. It's been cataloged, studied, photographed. It orbits the sun roughly once every 133 years, swinging out beyond the orbit of Pluto, before returning to pass inside Earth's orbit. Its next close approach to Earth won't happen until August of 2126, more than a century from now. So why should you care about something that won't arrive until your great-great-grandchildren are old? Because Swift Tuttle isn't some tiny rock like Apophis. It's not even in the same category. Apophis is approximately 370 meters across. 3i Atlas, at its most generous size, estimates might be 3.5 kilometers in diameter. Swift Tuttle is 26 kilometers wide. That's 16 miles of primordial ice and rock, a mountain flying through space at over 60 kilometers per second. To put that in perspective, if Swift Tuttle were a city, it would be larger than Paris. If it were a mountain, it would be taller than Mount McKinley. And it's coming back. Not tomorrow, not next year, but it's coming. And when it arrives in 2126, it will pass within about 23 million kilometers of Earth. That might sound like a comfortable margin, and by the standards of 2126, it will be. But orbital mechanics are not static things. Gravitational perturbations from Jupiter and other planets can nudge trajectories over time. What seems safe today might not be safe in 300 years, or 600, or 1,000. And this is where the mathematics become genuinely unsettling, because Swift Tuttle doesn't just have size on its side. It has something worse. The story of how we found 3i Atlas begins with a telescope system that scans the sky every night, hunting for anything that moves. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes designed specifically to find dangerous asteroids before they find us. On July 1st, 2025, ATLAS spotted something moving unusually fast against the background stars. Within days, astronomers calculated its trajectory and realized what they'd found. This wasn't an asteroid from our solar system. This was something from outside, something that had traveled the gulfs between stars. The object brightened as it approached the sun, developing a fuzzy coma of gas and dust around its nucleus, confirming it was a comet rather than an asteroid. Estimates of its size range widely, but even the most generous calculations put it at perhaps 3.5 kilometers across. That's large by everyday standards, certainly, but small by extinction event standards. Its trajectory showed unmistakable signs of being hyperbolic, meaning it was moving too fast to be captured by the sun's gravity. It would make its closest approach to Earth around December 19th, 2025, passing at about 1.8 astronomical units before escaping our solar system forever. Scientists mobilized every available telescope to study it. The Hubble Space Telescope captured images showing its developing tail. The European Space Agency's JUICE spacecraft, currently on its way to Jupiter, turned its instruments toward 3i Atlas to gather additional data. Ground-based observatories recorded spectra, analyzing the light reflected from its surface to determine its chemical composition. What they found was simultaneously familiar and alien. The comet showed signs of water ice and carbon dioxide, the same materials that make up comets from our own solar system, but in slightly different ratios that might hint at its exotic origins. The physics of 3i Atlas are straightforward. As it approaches the sun, solar radiation heats its icy nucleus, causing frozen materials to sublimate directly from solid to gas. This outgassing creates the coma, the fuzzy cloud surrounding the nucleus, and eventually forms the characteristic tail that always points away from the sun, pushed by solar wind and radiation pressure. There's nothing anomalous here, nothing that defies known physics. It's simply a comet from another star system, following the same physical laws that govern comets everywhere. But while 3i Atlas captures attention, Swift-Tuttle waits in the outer darkness of our solar system, slowly making its way back toward us. Its orbit takes 133 years to complete, give or take, and it's currently somewhere out beyond the orbit of Uranus. Too far and too faint to be seen, except by the most powerful telescopes. But we know it's there, and we know exactly where it's going, because Newton's laws of motion don't care whether we're paying attention or not. Swift-Tuttle last passed through the inner solar system in 1992. Astronomers captured images of it then, measuring its size, estimating its mass, calculating its trajectory with increasing precision. They determined it would return in 2126, and they calculated how close it would come to Earth. The answer was about 60 times the distance between Earth and the Moon. That sounds safe, and by the standards of 2126, it probably is. Current NASA and JPL simulations show no probability of collision during that pass. But here's where orbital mechanics become genuinely complex and genuinely worrying. Swift-Tuttle's orbit intersects Earth's orbit. Not now, not in 2126, but it intersects. We cross paths with this comet's orbital path twice a year, in fact. Every August, Earth plows through the debris stream left behind by Swift-Tuttle during its previous passages through the inner solar system. This debris creates the Perseid meteor shower, one of the most reliable and spectacular annual meteor displays. Those shooting stars you see every summer, that's Swift-Tuttle saying hello. But debris and the comet itself are two very different things. The comet's orbit is not fixed in stone. It's subject to gravitational perturbations, primarily from Jupiter, the solar system's gravitational bully. Jupiter's enormous mass can nudge the orbits of comets over time, sometimes by small amounts, sometimes by catastrophic amounts. These perturbations are predictable in the short term, but become increasingly uncertain over longer timescales. Calculating where Swift-Tuttle will be in 2126 is straightforward. Calculating where it will be in 25-26 is much harder. Calculating where it will be in 35-26 involves so many variables and potential perturbations that predictions become increasingly unreliable. Scientists have run simulations projecting Swift-Tuttle's orbit thousands of years into the future. Some of those simulations show the comet passing harmlessly by Earth, over and over, century after century. But some simulations show something else. They show orbital resonances with Jupiter slowly shifting Swift-Tuttle's path, bringing it incrementally closer to Earth with each pass. They show scenarios where, far in the future, the comet's orbit and Earth's orbit intersect not in space, but in time. This is speculation. Absolutely. No scientist can tell you with certainty what will happen in the year 4000. The mathematics of orbital mechanics become a probability cloud rather than a definite prediction once you extend your timeline far enough into the future. But the mere fact that those simulations exist, that they're mathematically possible, that there are trajectories where this enormous comet and our planet occupy the same point in space at the same moment in time, should make Swift-Tuttle worthy of significantly more attention than it currently receives. And then there's the matter of the orbit's orientation itself. Most asteroids and comets orbit the Sun in the same direction Earth does, in what's called a retrograde orbit. They move with the flow of the solar system's primordial rotation. Swift-Tuttle does not. It orbits in the opposite direction, in a retrograde orbit, meaning it moves against the flow. This seemingly technical detail has profound implications, because it means that if Swift-Tuttle and Earth ever did meet, they wouldn't be traveling in roughly the same direction, like cars merging on a highway. They would be moving toward each other head-on, like a game of chicken played at cosmic velocities. And that changes everything. Imagine two cars colliding. In a rear-end collision, where both cars are moving in the same direction and one is simply moving faster, the relative velocity at impact might be 10 or 20 miles per hour. Damage occurs certainly, but it's often survivable. Now imagine a head-on collision where both cars are moving toward each other at 60 miles per hour. The relative velocity at impact is 120 miles per hour, and the results are catastrophic. The kinetic energy released during a collision scales with the square of velocity, which means doubling the speed doesn't just double the energy, it quadruples it. Now, scale that up to cosmic proportions. Earth orbits the Sun at approximately 30 kilometers per second. Swift-Tuttle, moving in its retrograde orbit, travels at roughly 60 kilometers per second. If they met head-on, the relative impact velocity would be around 90 kilometers per second. That's over 200,000 miles per hour, or roughly 0.03% of the speed of light. At that velocity, the kinetic energy released would be so enormous that it defies comfortable comprehension. Kinetic energy is calculated as 1/2 times mass times velocity squared. Swift-Tuttle's mass is estimated at approximately 213 billion tons. Multiply that mass by the square of 90 kilometers per second, and you get an energy release of roughly 840 trillion joules, or about 200 million megatons of TNT equivalent. To put that in perspective, the asteroid that killed the dinosaurs 66 million years ago released approximately 100 million megatons. Swift-Tuttle, because it's both larger and moving faster, would release roughly twice that energy, though some calculations accounting for the head-on geometry suggest it could be significantly higher. What would that actually mean for Earth? Let's walk through what scientists think would happen in the first seconds, minutes, hours, and days after impact, keeping in mind that these are models, approximations based on physics and computer simulations, not empirical observations, because thankfully, nobody has ever witnessed an extinction-level impact and lived to measure it. At the moment of contact, Swift-Tuttle would punch through Earth's atmosphere in less than a second. The atmosphere would provide approximately as much resistance as tissue paper provides to a bullet. The comet would strike the surface, likely an ocean given that oceans cover 70% of our planet, and in that instant, several things would happen simultaneously. The kinetic energy of the impact would convert almost instantaneously into heat and shock waves. The comet itself would vaporize, along with a chunk of Earth's crust larger than a major city. Material would be ejected upward at velocities exceeding escape velocity, meaning some of Earth's crust would be blasted into space, never to return. Other material would arc high into the atmosphere before falling back as molten debris, igniting fires across entire continents. The impact crater would be enormous, perhaps 200 kilometers across, and 30 kilometers deep, excavating into Earth's mantle. If the impact occurred in an ocean, it would create tsunamis unlike anything in recorded human history. Waves potentially kilometers high would radiate outward at the speed of sound in water, scouring coastlines on every continent. If the impact occurred on land, the shockwaves would trigger earthquakes measuring beyond the capability of our current seismic scales, collapsing structures thousands of kilometers from ground zero. But the immediate devastation at the impact site would be only the beginning. The real catastrophe would unfold over the following hours and days as millions of tons of pulverized rock and vaporized comet material fell back through the atmosphere. This debris, superheated by atmospheric entry, would radiate thermal energy downward, effectively turning Earth's atmosphere into a global oven. Models suggest that the infrared radiation from re-entering ejecta could be intense enough to ignite forest fires simultaneously across the entire hemisphere facing the impact. Animals caught in the open would be roasted alive within minutes. Then comes the impact winter. The dust and ash lofted into the upper atmosphere would block sunlight for months, possibly years. Photosynthesis would cease. Temperatures would plummet. The base of the food chain would collapse, and everything above it would follow in cascading extinctions. Marine ecosystems would fare slightly better than terrestrial ones, but not by much. Acid rain from sulfur compounds and nitrogen oxides would acidify the oceans, dissolving carbonate structures like coral reefs and the shells of countless marine organisms. Scientists debate the exact details of these scenarios. Some models suggest more ash and longer winters. Others calculate shorter disruptions, but more intense thermal pulses. The truth is that we're extrapolating from limited data, studying ancient geological records of past impacts, and running computer simulations based on our best understanding of atmospheric physics, geology, and climatology. But every model, regardless of the specific parameters, arrives at the same basic conclusion. An impact from Swift Tuttle would constitute a mass extinction event potentially worse than the one that ended the Cretaceous period and wiped out the dinosaurs. It would fundamentally alter the trajectory of life on Earth. And here's what makes this genuinely unsettling, rather than merely academically interesting. Swift Tuttle exists. It's not a theoretical construct or a worst-case scenario dreamed up by pessimistic scientists. It's real. It's massive. It's fast. It's in a retrograde orbit, and it crosses Earth's orbital path. The question isn't whether Swift Tuttle is dangerous. The question is whether we'll ever find ourselves in the same place at the same time, and whether we'll see it coming if we do. So why aren't we talking about this? Why isn't Swift Tuttle dominating headlines the way 3i Atlas and Apophis are? Perhaps because 2126 feels safely distant, someone else's problem. Perhaps because the human mind struggles to engage with threats that won't manifest for generations. Or perhaps because acknowledging that something this dangerous exists with no current means of deflecting it if it were on a collision course is simply too uncomfortable to think about for very long. But think about it we must, because the first step in addressing any danger is acknowledging that it exists. Every August, you can step outside after midnight, look up at a dark sky away from city lights, and watch Earth collide with Swift Tuttle. Well, not the comet itself, but the river of debris it's left behind over millennia of passages through the inner solar system. These collisions produce the Perseid meteor shower, one of the most spectacular annual astronomical events visible from Earth. Under ideal conditions, you might see 60 or more meteors per hour, bright streaks of light scratching across the darkness as particles no larger than grains of sand slam into Earth's atmosphere at 200,000 kilometers per hour and vaporize in brilliant flashes. This happens every year. It's reliable, predictable, and beautiful. It's also a constant reminder that Swift Tuttle's orbit intersects Earth's orbit. We're already interacting with this comet, just not with the comet itself. We're plowing through the debris field it's scattered across its orbital path, like breadcrumbs marking the trail of a giant. The Perseid meteor stream stretches along Swift-Tuttle's entire orbit, a diffuse cloud of dust and small rocks distributed across millions of kilometers of space. When Earth passes through this stream each August, we're essentially flying through a cosmic sandblaster. The individual particles are tiny, most no bigger than a pebble, but they're moving at relative velocities of roughly 60 kilometers per second. At that speed, even a grain of sand carries significant kinetic energy. Most burn up harmlessly in the upper atmosphere, creating the light shows we associate with shooting stars. Occasionally, larger fragments make it deeper into the atmosphere, creating brilliant fireballs that can be seen for hundreds of kilometers. Scientists study these meteor streams carefully, not just for their beauty, but for what they reveal about the parent comet. By analyzing the chemical composition of meteor spectra, researchers can infer the composition of Swift-Tuttle itself. By measuring the spatial distribution of particles in the stream, they can reconstruct the comet's historical activity, determining when it was more or less active, when it shed more or less material. It's like forensic science applied to comets, reading the clues left behind to understand the object that created them. But meteor streams also raise interesting and occasionally alarming questions. The density of particles in a meteor stream isn't uniform. There are clumps and gaps, regions where the debris is more concentrated, and regions where it's sparse. This structure develops over time as gravitational perturbations from planets push particles around, clumping some together and scattering others. In some years, Earth passes through a denser region of the Perseid stream, producing meteor storms rather than showers, with hundreds or even thousands of meteors visible per hour. Could Earth ever encounter a particularly dense clump of Swift-Tuttle debris, dense enough to pose an actual hazard rather than just a spectacular show? This question has been raised in various astrophysics communities, including speculative discussions on platforms like Reddit, where amateur astronomers and enthusiasts share ideas, theories, and concerns. Some posts suggest that Earth might pass through unusually dense Swift-Tuttle debris streams in 2028 or 2030, potentially causing meteor storms more intense than typical Perseid displays. These claims circulate with varying degrees of supporting evidence, often mixing legitimate astronomical observations with speculation and sometimes outright misinformation. It's important to distinguish between scientific predictions and internet speculation. Professional astronomers have not issued warnings about hazardous meteor storms in 2028 or 2030. The Perseids will continue, as they always have, producing their annual display without posing any danger to anyone on the ground. The atmosphere is an excellent shield against small particles. Even during the most intense meteor storms ever observed, no one has been injured by meteors reaching the ground. The risk is essentially zero for people on Earth's surface. However, spacecraft are a different story. In orbit, there's no protective atmosphere. Satellites and space stations travel through the same regions Earth does, and they're vulnerable to impacts from even tiny debris particles. A grain of sand hitting a satellite at 60 kilometers per second carries enough energy to damage sensitive instruments or puncture thin metal. During known meteor storms, satellite operators sometimes adjust orbits or orient spacecraft to minimize cross-sectional area, reducing the probability of a damaging hit. Space agencies monitor meteor stream predictions carefully and take precautions when necessary. But this raises a broader point about risk perception and communication. When people hear about meteor streams or comet debris, they often misinterpret what these terms mean. A tail structure extending millions of kilometers from a comet sounds ominous, conjuring images of a cosmic weapon or some kind of directed energy. In reality, comet tails are extraordinarily diffuse, more vacuum than matter. You could fly a spacecraft through most comet tails without even noticing. The coma, the fuzzy cloud surrounding the nucleus, is similarly tenuous. What looks solid and threatening in telescope images is actually less dense than the best laboratory vacuum we can create on Earth. This disconnect between perception and reality fuels misunderstanding. People see images of 3I Atlas with its developing tail and imagine danger. They read about debris streams and picture hazardous clouds of rocks hurtling toward Earth. They encounter unfamiliar astronomical terminology and fill in the gaps with assumptions that feel intuitive but are scientifically incorrect. Dust streams become incoming threats. Orbital intersections become collisions. Possibilities become certainties. Scientists, for their part, often struggle to communicate these nuances effectively. They speak in probabilities and confidence intervals, in careful hedges and precise qualifications. They say things like, current models show no significant probability of collision in the next century, when what people hear is, so you're saying there's a chance. They publish papers discussing long-term orbital uncertainties, and those papers get distilled into headlines screaming about potential doom. The gap between what science says and what people hear grows wider with each round of telephone, until speculation becomes narrative and narrative becomes belief. This is why understanding the difference between constant background risk and discrete catastrophic risk matters. The debris from Swift-Tuttle produces a constant low-level interaction with Earth every August. It's been happening for thousands of years and will continue happening for thousands more. It's not a threat. It's just physics, the natural consequence of Earth's orbit intersecting a comet's orbital debris field. But the comet itself, the 26-kilometer nucleus from which all that debris originated, represents a discrete risk. It's not constant. It's not background. It's a specific object on a specific trajectory, and if circumstances aligned in a particular way, it could become genuinely catastrophic. Conflating these two types of risk leads to confusion. It leads to people either panicking about things that don't matter or dismissing things that do. And it leads to situations where the real monster goes unnoticed while everyone panics about shadows. The internet is a remarkable tool for sharing information, but it's also an amplifier for misunderstanding. A feedback loop where speculation becomes increasingly divorced from reality with each iteration. Nowhere is this more apparent than in discussions about astronomical objects, particularly ones with unusual characteristics or threatening names. 3I Atlas, being both interstellar and mysterious, has become a magnet for conspiracy theories, wild speculation, and outright fabrication. Start with the most benign misunderstandings and work outward toward the truly bizarre. Some people genuinely believe that 3I Atlas is hidden from public view, that images and data are being suppressed by government agencies or scientific institutions. This conspiracy theory rests on a fundamental misunderstanding of how modern astronomy works. There are thousands of amateur astronomers with sophisticated equipment scanning the sky every night. Professional observatories share data almost immediately through international networks. Suppressing information about a comet would require coordinating silence among thousands of independent observers across dozens of countries, many of which have conflicting political interests. It would be essentially impossible, and more importantly, there would be no reason to do it. 3I Atlas poses no threat, so there's nothing to hide. Then there are theories about the comet's composition and origin. Avi Loeb, a respected astrophysicist at Harvard who has gained notoriety for proposing unconventional ideas about interstellar objects, has speculated publicly about whether 3I Atlas or previous interstellar visitors like Oumuamua might exhibit characteristics suggesting artificial origin or unusual construction. To be clear, these are speculations, not conclusions. Loeb himself emphasizes the need for more data and careful analysis. But in the translation from scientific speculation to internet discourse, nuance gets lost. What begins as, we should consider all possibilities, including unconventional ones, becomes Harvard scientist claims comet is alien spacecraft in clickbait headlines, which then becomes comet is definitely alien spacecraft in social media discussions. Reddit threads devoted to 3i Atlas contain hundreds of posts analyzing images, debating interpretations, and constructing elaborate narratives. Some claim that tail structures show evidence of controlled propulsion. Others point to brightness variations as signs of intelligence or artificial manipulation. A few suggest that the comet is actually a surveillance device sent by an extraterrestrial civilization to observe our solar system. These ideas range from creative misinterpretation of real data to pure fantasy untethered from any empirical observation. Why do these theories proliferate? Part of the answer is that space is genuinely weird and counterintuitive. Objects millions of kilometers away appear as tiny points of light. Their behavior is governed by physics that feels alien to our everyday experience. When you combine that inherent strangeness with incomplete information and the human tendency to pattern match, you get fertile ground for misinterpretation. A comet brightens as it approaches the sun? That's outgassing from solar heating, a well-understood process. But if you don't know that, it might look like the object is activating or powering up. A comet's tail changes shape and orientation. That's the result of solar wind and orbital geometry. But if you're looking for signs of propulsion, you'll find them, even where they don't exist. Then there are conspiracy theories about institutional silence and communication failures. Some online communities claim that space agencies are aware of danger from 3i Atlas or other objects, but are deliberately withholding information to prevent panic. This theory makes a certain emotional sense. After all, if a civilization-ending threat were approaching, would governments really tell us? Or would they keep quiet to maintain order for as long as possible? The answer, almost certainly, is that they would tell us, because maintaining a conspiracy of that magnitude would be impossible. Scientists talk to each other. They publish papers. They present at conferences. They have families and friends and colleagues outside their immediate institutions. Keeping everyone quiet about an incoming extinction-level threat would require a level of coordination and compartmentalization that has never been achieved in human history. Moreover, the scientific community is international, politically diverse, and often contentious. Expecting global agreement on suppressing information assumes a unity that simply doesn't exist. But perhaps the real communication failure isn't about conspiracy or suppression. Perhaps it's about priority and emphasis. Space agencies do communicate, but they communicate what they consider important. 3i Atlas gets attention because it's scientifically interesting, because it's an interstellar visitor offering a glimpse into the chemistry and dynamics of other planetary systems. It gets studied, photographed, analyzed, and discussed. Apophis gets attention because its close approach in 2029 will be a spectacular observational opportunity and a valuable test of planetary defense systems. Swift-Tuttle, meanwhile, gets a brief mention every August when the Perseids light up the sky, and then it fades back into obscurity. It's not urgent. It's not immediate. It won't return for another century. So it doesn't make headlines, doesn't trend on social media, doesn't capture public imagination the way mysterious interstellar visitors do. This is the real communication failure. Not conspiracy, not suppression, but simple prioritization. We focus on what's novel and immediate at the expense of what's genuinely dangerous but distant. We scan the horizon for unfamiliar threats while ignoring the known danger that's simply taking its time to arrive. It's the same cognitive bias that leads people to fear airplane crashes while ignoring the much greater risk of car accidents. The unfamiliar captures attention. The familiar, even when it's more dangerous, fades into background noise. And so we have millions of people scrutinizing 3i Atlas, debating whether it poses some hidden threat, while Swift-Tuttle waits patiently in the outer solar system, genuinely worthy of attention, but receiving almost none. The internet amplifies the wrong signal. Clickbait prioritizes the wrong risk. And the conversation continues, loud and passionate and utterly misdirected. If we're going to have a mature, rational discussion about cosmic threats, we need to start by understanding what actually poses a threat and what doesn't. We need to distinguish between speculation and fact, between possibility and probability, between what's interesting and what's dangerous. And we need to acknowledge that the most dangerous object in our solar system isn't some mysterious interstellar visitor. It's a comet we've known about for over a century and a half, one that returns predictably, one that crosses our orbital path, and one that we should be watching far more carefully than we are. While Swift-Tuttle lurks in the distant outer solar system, 3i Atlas continues its journey through our cosmic neighborhood, providing astronomers with an unprecedented opportunity to study an object from beyond our solar system in real time. Recent observations have revealed details that both confirm our understanding of comet physics and hint at the profound strangeness of material born around other stars. The Hubble Space Telescope, orbiting Earth above the distorting effects of our atmosphere, has captured some of the sharpest images yet of 3i Atlas. These images show a well-defined coma surrounding the nucleus, along with the beginning of a tail structure extending away from the Sun. The coma appears greenish in some wavelengths, a color produced by diatomic carbon molecules breaking down in sunlight. This green glow is common in comets from our solar system, a reassuring sign that the basic chemistry of this interstellar visitor isn't wildly different from local objects. Ground-based observatories have also been tracking 3i Atlas intensively. As it approaches perihelion, its closest point to the Sun, solar heating has caused the comet to brighten substantially. Observatories in Chile, Hawaii, and across Europe have recorded spectra showing not just carbon compounds, but also water vapor and carbon dioxide, confirming that this object contains the same volatile materials that make up comets born in our solar system. This similarity is simultaneously comforting and thought-provoking. It suggests that the processes that formed our solar system 4.6 billion years ago weren't unique, that other star systems underwent similar formation sequences, creating similar mixtures of ice, rock, and organic compounds. The European Space Agency's JUICE spacecraft, currently on its multi-year journey to Jupiter, took advantage of 3i Atlas, passing relatively close to its flight path to turn its instruments toward the comet. Though JUICE's primary mission is studying Jupiter's moons, its cameras and spectrometers are sophisticated enough to contribute valuable data about this unexpected target of opportunity. The spacecraft observed 3i Atlas from a different angle than Earth-based telescopes, providing stereo observations that help scientists construct three-dimensional models of the coma structure and outgassing patterns. But beyond the immediate observations of 3i Atlas, this encounter raises profound questions about interstellar objects more generally. How common are they? How many pass through our solar system undetected because they're too small, or too dark, or simply in the wrong part of the sky when we're looking? Oumuamua, discovered in 2017, was probably only detected because its elongated shape made it tumble in a way that caused dramatic brightness variations. Borisov, discovered in 2019, was found because it developed a noticeable coma as it approached the Sun, making it bright enough to spot. 3i Atlas was found by a dedicated survey system specifically designed to detect moving objects. How many interstellar visitors have passed through unnoticed because none of these conditions were met? Statistical models suggest that there might be thousands of interstellar objects passing through the inner solar system at any given time, most too small or too dark to detect with current technology. The Planetary Society and other organizations have been advocating for improved survey systems, better telescopes, and more sophisticated detection algorithms, specifically to find these visitors from other star systems. Each one represents a sample of material from a potentially unique stellar environment, a chemical signature of planetary formation around other stars. A piece of evidence in the grand puzzle of how common Earth-like planets might be throughout the galaxy. None of these interstellar visitors have posed any danger to Earth. They're all on hyperbolic trajectories, meaning they're leaving and won't return. They're messengers, not threats, ambassadors from the vast spaces between stars, bringing news of cosmic chemistry and planetary formation far from our sun. Yet they serve another purpose beyond pure science. They're practice runs for planetary defense systems, opportunities to test detection networks, refine trajectory calculations, and improve coordination between observatories worldwide. When a genuinely dangerous object does appear, whether it's an interstellar interloper on a collision course or a solar system resident like Swift Tuttle arriving at the wrong time in the wrong place, we'll need every bit of practice we can get. Detection is the first step in any planetary defense strategy. You can't deflect what you haven't seen. You can't calculate trajectories for objects you don't know exist. Every interstellar visitor that gets detected, tracked, and analyzed makes the entire network slightly better at its job, slightly more likely to spot the next object, slightly more prepared for the day when preparation actually matters. And make no mistake, that day will eventually come. Not necessarily tomorrow, not necessarily in our lifetimes, but eventually. Earth has been bombarded by asteroids and comets throughout its history. The geological record preserves dozens of impact craters, and those are just the ones that survived erosion and tectonic activity. Many more impacts occurred in the oceans or on ancient surfaces, now buried beneath newer rock. The question isn't whether Earth will experience another major impact. The question is when, and whether we'll see it coming. 3i Atlas and other interstellar visitors remind us that space is not empty and static. It's full of objects moving at enormous speeds, crossing paths, occasionally colliding, constantly redistributing matter and energy across the cosmos. Our solar system is not isolated. We're part of a galaxy containing hundreds of billions of stars, each potentially surrounded by its own system of planets and comets, some of which occasionally get ejected into interstellar space to wander for millions or billions of years before encountering another star system. We've detected 3 so far. There will be more, and each one is an opportunity to learn, to prepare, to practice the skills we'll need when something genuinely dangerous appears. But while we practice on harmless interstellar visitors, while we refine our techniques on objects that pose no threat, we should perhaps spare some attention for the known dangers that don't require any detection because we've already found them. Swift Tuttle isn't hidden. It's not mysterious. We know where it is, where it's going, and when it will arrive. What we don't know, with the certainty we'd prefer, is where it will be 1,000 years after that, or 2,000, or 10,000. And that uncertainty, that gap in our knowledge about an object we've known about since 1862, should concern us far more than speculation about interstellar visitors that won't even come close to Earth. While comets and asteroids capture headlines with their potential for catastrophe, the broader universe continues to reveal itself in ways both beautiful and unsettling, each discovery adding context to our understanding of cosmic risk and our place in an incomprehensibly large and active galaxy. Recent breakthroughs across multiple fields of astronomy demonstrate how rapidly our knowledge is expanding and how much we still don't understand about the universe we inhabit. Artificial intelligence is revolutionizing astronomy in ways that would have seemed like science fiction just a decade ago. Researchers at the University of Oxford have developed AI systems capable of classifying transient cosmic events with accuracy matching or exceeding human experts, but doing so thousands of times faster. These systems can analyze images from telescopes, identify supernova, gamma-ray bursts, variable stars, and potentially hazardous asteroids, and alert astronomers to objects requiring immediate follow-up observation. This isn't just academic convenience, it's a force multiplier for planetary defense. Every hour saved in detection and classification is an hour gained in trajectory calculation and potential response. When an asteroid is heading toward Earth, time is the most precious resource. AI systems that can process data instantaneously rather than waiting for human review could mean the difference between successful deflection and impact. The technology is improving rapidly. Current systems can distinguish between asteroids, comets, spacecraft, and artifacts in images with remarkable reliability. They can predict which newly discovered objects are likely to be interesting or dangerous based on preliminary trajectory data. They can even help predict meteor shower intensity by analyzing historical patterns and current comet positions. As these systems become more sophisticated and more widely deployed, our ability to monitor the sky for threats improves correspondingly. We're moving toward a future where nothing of significant size approaches Earth unnoticed, where every potential impact risk gets flagged immediately, where planetary defense systems have maximum warning time to develop response strategies. Meanwhile, the James Webb Space Telescope continues to probe the atmospheres of exoplanets, revealing worlds stranger than science fiction writers imagined. Recent observations of ultra-hot Jupiter planets have shown atmospheric tails extending millions of kilometers behind these worlds, streams of atmospheric material being stripped away by intense stellar radiation and powerful stellar winds. These planets orbit so close to their parent stars that their atmospheres are literally boiling away into space, creating comet-like tails of hydrogen, helium, and heavier elements trailing behind them as they orbit. This might seem disconnected from asteroid impacts and planetary defense, but it's intimately related to understanding how planets survive in harsh environments. These ultra-hot Jupiters are losing atmosphere at prodigious rates, yet they continue to exist, meaning they either formed with truly enormous atmospheres or they're being somehow replenished. Understanding this balance between loss and retention helps scientists model how atmospheres respond to extreme events, including major impacts. When a comet like Swift-Tuttle strikes a planet, enormous amounts of atmosphere can be ejected into space, heated to temperatures that allow it to escape the planet's gravity entirely. Models of atmospheric loss during impacts draw on the same physics being observed at ultra-hot Jupiters, where the process happens continuously, rather than catastrophically. Closer to home, new observations of novae on white dwarf stars have revealed complexity in stellar explosions that challenges existing models. White dwarfs are the end state of stars like our Sun, stellar corpses no longer undergoing fusion in their cores. When a white dwarf is part of a binary system, it can gravitationally steal material from its companion star. This stolen material accumulates on the white dwarf's surface until pressure and temperature trigger a thermonuclear explosion called a nova. Recent close-up images captured during nova events show that the material isn't ejected uniformly. Instead, it's expelled in complex patterns, clumps, and streams shaped by magnetic fields and rotational dynamics. These observations have implications for understanding explosive events generally, including impact events, where material is ejected at high velocities in patterns shaped by angle of impact, composition, and target properties. Looking forward, upcoming missions promise to revolutionize our understanding of the solar system and our ability to detect threats. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will have a field of view 100 times larger than Hubble's, allowing it to survey enormous swaths of sky rapidly. It will detect asteroids, comets, and other solar system bodies with unprecedented efficiency, dramatically increasing the catalog of known objects and improving our statistical understanding of impact risks. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s with a massive telescope designed specifically for surveying the entire visible sky repeatedly. Its primary science goals include mapping the solar system's small body population with completeness never before achieved. These systems will find tens of thousands of new asteroids and comets. Most will be harmless, their orbits taking them nowhere near Earth. But statistics guarantee that some will be potential impactors, objects whose trajectories bring them close enough to Earth to warrant monitoring, and eventually, perhaps, intervention. Each discovery improves our understanding of the overall population, refining statistical models of impact frequency, and helping prioritize resources for deflection technology development. But telescopes and AI systems can only tell us what's there and where it's going. They can't change trajectories. They can't prevent impacts. For that, we need deflection technology, and here the news is more mixed. NASA's DART mission successfully demonstrated kinetic impactor technology in 2022, deliberately crashing a spacecraft into a small asteroid and measuring how much its orbit changed. The experiment worked, proving that humans can nudge asteroid trajectories given sufficient warning time. But DART hit a tiny asteroid with minimal gravitational binding. Swift-Tuttle is millions of times more massive, a solid nucleus held together by its own gravity and moving at enormous velocity. Deflecting something that large would require technology we don't currently possess, energy budgets beyond our current capabilities, and decades of warning time to implement any realistic strategy. This is the uncomfortable truth lurking beneath all the technological optimism and scientific progress. We're getting better at finding threats. We're improving our ability to predict trajectories and assess risk. But our capacity to actually prevent a catastrophic impact from a comet like Swift-Tuttle remains theoretical at best. We have ideas, concepts, simulations. We don't have tested, proven, deployable systems capable of handling an object of that scale. And we won't develop those systems unless we acknowledge the threat and commit resources to addressing it. 3i Atlas is a wonder, an opportunity for science, a practice target for detection networks. Apophis will be a spectacular show in 2029, a close approach that harms no one while teaching us volumes about asteroid composition and dynamics. But Swift-Tuttle is the genuine article, the real challenge, the object that forces us to confront the limits of our current capabilities and the inadequacy of our long-term planning. It's massive, it's fast, it crosses our orbit, and it will return. Maybe not in our lifetimes, maybe not for centuries, but it will return. And when it does, we should have better answers than hope and prayer. The universe is not malicious, but neither is it benign. It simply is, operating according to laws of physics that care nothing for human survival or flourishing. Comets orbit, planets revolve, gravity pulls, momentum carries objects across vast distances. Sometimes those objects pass harmlessly, sometimes they collide, and when they do, the results are determined by mass, velocity, angle of impact, and nothing more. No intention, no mercy, no consideration of civilizations that might be in the way. We live in a shooting gallery, orbiting an ordinary star in an ordinary galaxy where impacts happen with statistical regularity. We've been fortunate so far, existing during a relatively quiet period in Earth's bombardment history. But quiet periods don't last forever. Eventually, the dice come up snake eyes. Eventually, an object arrives at exactly the wrong place, at exactly the wrong time. And when that happens, everything we've built, everything we've achieved, everything that makes us human could vanish in a flash of light and a cloud of dust. Just another extinction event recorded in geological strata for whatever comes after us to puzzle over. Or we could see it coming. We could track its approach, calculate its trajectory, plan a response, and execute a deflection with enough lead time to matter. We could be the first species in Earth's history to survive what should be an extinction event, not through luck or adaptation, but through applied knowledge and deliberate action. We could, in other words, choose our own fate rather than accepting whatever the cosmos randomly delivers. But that requires looking at the right threats, understanding real dangers rather than panicking about harmless objects, and maintaining focus on genuine challenges rather than temporary distractions. It requires ignoring the clickbait, dismissing the conspiracy theories, and paying attention to the mathematics. 3i Atlas is fascinating, but it's not dangerous. Apophis is spectacular, but it won't hit us. Swift-Tuttle is neither mysterious nor immediate, but it is genuinely, mathematically, physically capable of ending everything we know. And that, more than any other reason, is why we should stop looking at the wrong thing in the sky and start watching the real monster that everyone seems to have forgotten.